Okay, in this lecture, we're going to talk about acids and bases. And to start off with some general definitions, there's Arrhenius acids, Bronsted-Lowry acids, Lewis acids. But let's first just define an acid with something we're more familiar with. And an acid is something that tastes sour. Now, as we move forward in chemistry, you usually don't want to taste things, right, that you're using in the laboratory, but this is something we're familiar with. Vinegar tastes sour, so acids taste sour, right? And bases usually taste bitter or feel soapy. Okay, so that's sort of a quick way to figure out if something's an acid or a base, just in terms of our everyday sort of involvement. Now, in chemistry, of course, we don't want to have to go around licking things to figure out if they're an acid or base, so we have other formal definitions of acids and bases. And Arrhenius was one of the first to characterize acids and bases, and this is the same guy that gave us, rate constants and activation energy and temperature being all wrapped up in kinetics. But he also did a lot of work with acids and bases. He also predicted global warming. But his definition of an acid is a substance that, when you put it in water, it increases the amount of H+. Okay, so you add something to water, X plus H2O, and, there's going to be a net effect of H plus increasing. And similarly, a base is going to be something that, when you dissolve it in water, it increases the concentration of hydroxide ions. So we'll say Y plus H2O leads to OH minus increasing. So if you think about an acid, we could have a stereotypical acid like H plus, HCl. And so when we add that to water, you end up creating a lot of H plus, and that's because you're also breaking this into Cl minus. So this HCl, when we put it in water and it's aqueous, breaks up into H plus and Cl minus. And so the same way you could put, NaOH, sort of a prototypical base, right? When you put that in water and that's aqueous, well, this breaks up into OH minus and Na plus. Okay, so that's a very Arrhenius definition of acids and bases, but it really limits us to what we can define as an acid or base, because it has to be in water in aqueous solution. So the Bronsted-Lowry definition is a little bit more general, in that an acid is a proton donor, right? So it doesn't matter if the HCl is aqueous or not, or an acid is aqueous or not, but it's going to donate a proton. And again, it's about increasing H+. Remember, H+ here is nothing more than a hydrogen atom that's lost an electron, i.e. a proton. So that's a proton right there. A base is a proton acceptor. These are more general, right? An acid donates protons, a base accepts protons. They don't necessarily have to contain OH minus, right? Like they did in the definition of Arrhenius. So Bronsted-Lowry gives us some more flexibility. The base doesn't need to contain OH minus. You can have something like NH3, ammonia, that will be a Bronsted-Lowry base, but is not an Arrhenius base. Okay, so this is a example of a Bronsted-Lowry base. It'll accept a proton to make NH4 plus, but not an Arrhenius base. Okay, so these are some definitions we're going to use throughout the next couple lectures when we're talking about acids and bases. Now, water itself can act as a Bronsted-Lowry base, right, and accept a proton. And so a lot of what we'll be doing with acids and bases involves a water molecule. And so let's think back to our HCl molecule. If this is the acid that's donating a proton, well, that proton has to go somewhere, and it goes to H2O. And so what we make here, we'll be using a lot, this H3O plus. Okay, so the HCl donated, so we call that an acid because it donated H plus, right? We look at this water, well, this is accepting H plus, so that's our Bronsted-Lowry base. In the same way, NH3 here is accepting an H+, a proton, to make NH4+. Here instead, the water is donating H+, so that's our acid. Okay, so when H2O loses an H+, it makes OH-. When it gains an H+, it makes H3O+. All right, and what this is showing here is that our water can be amphiprotic, right? Kind of like amphibious, multiple uses here, protic for proton. So the water can either accept or donate the proton depending on what you're comparing it with, right? Something that really wants to get rid of its H+, water's accommodating. Something that really needs an H+, water's accommodating. And so this makes water amphiprotic. Now, we have some additional terminology to include here and add, and that's our definition of conjugate, right? And conjugate means joined together as a pair. So in any reaction we write, an acid-base reaction that is, there's going to be an acid, a base, it's an acid-base reaction after all, but there's also going to be a conjugate acid and a conjugate base. And so we can look at an example here, HNO2. If this is our acid, it's going to be donating an H+, so this will go away, and a plus charge will go away, so it should make NO2- here. That's what we should be making on the right, and there it is. So these two things we want to link together here that are related clearly and just differ by an H+. So this is our acid, it's giving up the H+. The thing it creates is the conjugate base. Now, likewise, the water here is going to be our base that accepts the proton. And so when it accepts a proton, it turns into a conjugate acid. Right? So there's always going to be these pairs. You can draw these arrows to link them up and know that an acid and a base is going to be accompanied by the corresponding conjugate base and conjugate acid. And we introduced this H3O+ on the previous slide, but I just want to make the point here because you might see it in text. It's called hydronium. Okay, so this is water, H2O, neutral. This is hydronium ion. It's an ion, it's charged. Always H3O+. Now, in shorthand, right, you might see this written as hydronium. You might see it written as H3O+, or you might see it just written as H+. Right, so it depends if the water is specified. So I just want to give you a point of warning here that maybe I could just write, instead of HNO2 plus water, you might just see HNO2 aqueous, so we know it's in water, that is falling apart to H+ and NO2- aqueous. So what's written down here is a little bit more formal because we're sort of keeping track of all the molecules here, water and hydronium. But this is sort of a shortcut here that you'll see. NO2, we know it's in water. Everything's going to be in water here. And this thing is falling apart to H+ and NO2-. So, be on the lookout for all these things really being pretty interchangeable depending on the context. So let's do a little practice problem for a second. Feel free to pause the video here and try it yourself. Otherwise, I'm going to go forward and solve it. So, which of the following is a conjugate base of HPO4 2-? And so this might help to write out. If I'm looking for the conjugate base of this, then that implies this right here is the acid. And so if this is an acid, it's going to donate, here's where the shorthand comes in, it's H+. And so what is this without H+? PO4 3-. And all these things would be aqueous in this case. So sometimes it helps to try to write it out as a reaction. Which of the following is a conjugate base of this? Remember, there's always a pair. Conjugate base is paired with an acid. So the conjugate base of this implies it's an acid, which implies it donates a proton. PO4 2-, once we get rid of the H and a plus, will become PO4 3-. So the answer here should be 3. Now, you can have a lot of different acids and bases, and let's sort of order their strengths. And we'll go into this in more detail in future videos, but there's going to be strong acids, weak acids, and things that aren't really an acid at all, more of a base. Right? In the same way, there's going to be strong bases, weak bases, and then things that aren't really very basic at all. Okay, so above, this line right here, where water is the base, these are the strong acids, right? That's what's shown here. And so since they're strong acids, they donate their proton really, really, really well, which means their conjugate bases do not really act as a base. So if these are floating around in water, they're not really going to be able to take an H plus from water, right? They're not going to be able to accept an H plus from water, because if Cl minus here accepts an H plus, that would make HCl. But we just said HCl is a strong acid. It is always wanting to dissociate and get rid of that H plus. Okay. Now down here, bases below here, vice versa. These bases below where water acts as an acid are strong bases. Okay. So their conjugate acids do not act as acids in water. These things don't really go around donating protons in water, because if they did, they would make these, and these are strong bases, which would go around and steal immediately an H plus right back. Okay, so these acids don't really act as acids floating around in water. They're not, donating protons. These are the strong bases that freely accept protons. Okay, now all these things in the middle, there's obviously going to be a lot more weak acids and weak bases. And so these weak acids sometimes donate their protons, and these weak bases sometimes accept protons, and it depends on the context, what they're paired with, how exactly they're going to behave. And so this is, really a conjugate acid-base pairs chart. Okay, so this is listing here the conjugate acid-base pair. All right, so we can go back and look at our previous example here. HPO42 minus, well, when it's an acid, that's right here. So there's the conjugate base. So all of these pairs in here just differ by an H plus. Now, the strength in that chart, right, shows us the order of when these things are going to behave like acids and bases. Strong acids, always going to behave like an acid. Strong bases, always like a base. But for these weak acids and weak bases, it's a little bit more complicated, and you have to compare. Every acid-base reaction transfers a proton from the stronger acid to the stronger base. Okay? Proton from stronger acid to the stronger base. Okay? And we're always forming a weaker acid and weaker base. So you'll note in all of these reactions here, we're using a double arrow because it is an equilibrium. All right? There is an equilibrium here. What we're really wondering here is, where does the equilibrium lie? It's always going to lie with the proton, being transferred from the stronger acid to the stronger base. So an example like this, this is pretty straightforward because we just identified HCl as a strong acid. So we know equilibrium is going to favor this transferring its proton. Okay? So equilibrium is going to lie way over here to the right, because these things, Cl minus isn't going to act like a base and accept a proton and go back this way. So equilibrium lies to the right. Right? We've transferred the proton from the stronger acid to the stronger base. Another way of saying this is that, this water here, if this is an acid, HCl, then this is a base, water. And we can compare this base, water, with the conjugate base of HCl. This is a base, Cl minus. And we can see, okay, what's the stronger base, water or Cl minus? And so acids go stronger this way, stronger going up, but bases are getting stronger going down. Okay, so water is below Cl minus. Water is the stronger base, right? So we know that the equilibrium lies far to the right. Okay, because again, we're going to transfer the proton from the stronger acid to the stronger base, and equilibrium is going to lie with forming the weaker base. This is the weaker base, so equilibrium lies on the right. Okay, so let's look at another example here, right, where we have acetic acid and water making the acetate ion and the hydronium ion. So here we're going to Notice that this is acetic acid, right? If you want to look back at the chart, you can. It's right here. Okay, so this is our acid, which means this is our base. If this is our acid, then it without an H plus is our conjugate base. This must be the base, and this must be our acid. So now where does equilibrium lie? Well, we can compare the bases here if we wanted, and the equilibrium is going to lie with the weaker base. Okay, so let's go back and let's look at what is the weaker base. So bases get stronger going down. Here's CH3COO minus acetate. It is a weak base, but remember we're comparing it here to the other base involved. So we're comparing acetate to water, right? Here's acetate. It is stronger than water. So equilibrium should lie with the weaker base, right? And much the same way, we could look at the acids, acetic acid and H3O plus. Okay? Acetic acid and H3O plus. Equilibrium should lie with the weaker acid. H3O plus is up here. It's a stronger acid. So equilibrium lies with the weaker acid. So equilibrium here will lie with the weaker acid and the weaker base. Okay? So that means here, this is the weaker acid, this is the weaker base. So that means here that equilibrium is going to lie with the left side. Okay, so we still show it as a double-sided arrow, but we know most of this is going to be the reaction going to the left here. And we're going to have a lot more of this in our solution than we are the right side. Okay, so feel free to pause the video here and try to put into action on this practice problem what we just talked about. Feel free to pause the video here if you would like and try this question for yourself before I go forward and solve it. For the following proton transfer reaction, predict whether the equilibrium lies to the left or to the right. Okay, so the first thing we want to do here is go through and identify what are acids and what are bases. And we can consult this chart while we do so. Right? And we can look at the chart, but let's first just look at the reaction and see if we can identify for ourselves what is an acid and what is a base. So let's first look at this compound, HSO4, and let's find its partner, right? We can find its partner, its conjugate, it's going to be this, okay? And so the difference here is that this guy has lost an H+. So, that means this is an acid. It's donating an H+, which means this is a conjugate base. Right? Those are the pairs. That's what we're looking at. So if this is an acid, that must mean this is a base. But let's confirm. Let's find its pair. This has an H, so this base accepted an H+, and so that makes sense. So this is the conjugate acid to that CO3 2-, the base. And so now we know equilibrium is going to lie with the weaker acid and weaker base. So now we go through and we can look at the acid. So let's find HSO4 minus. Here it is. That's a pretty strong acid near the top of the chart. Stronger going up for acids, stronger going down for bases. So HSO4 is pretty high. Let's compare that to HCO3 minus, that conjugate acid. Let's replace that arrow. So let's compare the acids. So acid HSO4 minus, HCO3 minus. Which acid is stronger? HSO4, HCO3. So it looks like HSO4 minus is stronger than HCO3 minus. This is the weaker acid here. Equilibrium should lie on that side. Equilibrium should lie to the right. But let's confirm. Let's look at the bases because it should also lie with the weaker base. CO3 2- is here. SO4 2- is here. Remember, bases get stronger going down. Okay, so this is the weaker of the bases. And this is the weaker of the acids. So equilibrium lies to the right. Yes, because this is the weaker base and this is the weaker acid compared with this stronger acid and this stronger base. Okay, so that'll do it for this video where we talked about conjugate acids and bases and introduced the concept of an acid or base overall. Next video, we'll get into autoionization and talk more about the equilibrium constant of water before in future videos moving on to pH, strong acids, weak bases, and other types of acids and bases as well. That'll do it for this lecture. See you next time.